Hi everyone, this is Pokyung or B. I am taking care of the data engineering lead for our team, working for the Assignment 2. And today I will cover our predictive task definition and the data processing pipeline that made our models possible for the Assignment 2. So this is going to be the rating prediction on Amazon beauty reviews. And these are my teammates. And first of all, I'm going to introduce how we working on this data set. So we are predicting the user rating on Amazon beauty products, specifically given a user and an item, predicting the rating from 1 to 5 stars. This is a classic recommendation system problem solving that's relevant from our classwork. So the evaluation approach, we use the three metrics on for our testing. MSC, which is our primary metric, it heavily penalized the large prediction errors, and then RMSE. This is for interpretability. It's in the same scale as the ratings. And for the MAE, this is for the trying to understanding the typical error magnitude. So for the baseline comparison, our team implemented 4 baselines from the class material, which is the global mean, user mean, and item mean, and the bias model. So the bias model combines the global mean with the user and the item biases. And these establish performance floor before we moving on to matrix vectorization and multimodal approaches. And for the validation strategy, we use the 80-20 train test splits with fixed random seed 42. And then we are assessing the validity by comparing against these baselines and analyzing the prediction errors across different rating levels. And now let's move on to dataset overview. So we are using the Amazon reviews in 2023 dataset from the Beckley's lab at UCSD, specifically the all beauty category. So this dataset is publicly available for everyone, and this dataset contains the user reviews of the beauty products like makeup, skincare, and hair care items. So the data set purpose collection would be the reviews collected from the real customer purchases between 2018 to 2023. So each review is going to include the 1 to 5 star rating, user ID, and the item ID, and review text, optional images, and metadata like verified purchase status. So let's move into the original size of the data is 700,000 reviews, and there are hundreds and thousands of unique users and items, and then this representing the real world commercial behavior. So our challenge is going to be this data set is going to exhibit extreme sparsity. So most users rate very few items, and most items have very few ratings. So this creates the cold start problem where we have insufficient information to make the reliable prediction. That's where we introduce the K-core filtering system. And we are loading the raw data with JSON file. And after that, we are using the K equals 2, which means we are sorry, let's move on right here, which means we are removing users have fewer than 2 reviews, also removing items have fewer than 2 reviews, and then repeat this until we have the stable data set. And this is how our iteration progress throughout this data set. And in the final, we have about 72,000 reviews. This is about 10.3% retained. And the unique users, we have about 29,000. And the unique items, we have about 15,000. After that, we are ID mapping to create the integrated indices for users and items, and this is necessary for the matrix vectorization to index embedding efficiently. So after that, we are working on some statistic work, and you can see after the 80-20 train test splits, we are seeing these values, and then after we are testing these, we are saving files to these 5 categories for the later data processing. And you can see the mean and standard deviation, and then the range of the rating stars. And they're about 61.5% of the heavily skewed to 5 stars, and then towards the 1 star is about like a 10%. So there's really high sparsity of data, and then this explains why simple user mean and item mean baseline performs poorly. And that's where we are building the data loader Python files to process the image and then text the data later. And yeah, to summarize, the data pre-processing work delivered the filtering, the really heavy data set, and then proper 80-20 split for all models, and then reproducible pipeline. So the key takeaway from here is going to be about like 99% sparsity remains main challenge for the team, and then it's heavily biased for the 5-star reviews, and the median 2 to 3 reviews per user and item. Yeah, thank you for listening, and then let's move on to the next person.
So this is our basic pipeline for processing our image data. First, we set some parameters here. We're pixelizing the images, 32 by 32 pixel encoding. It's a little bit low, but if I have it too high, it just takes way too long to run. And then basically how it works is the images are stored as strings with URLs. So we parse out the URLs from those strings. It has a couple URLs for different resolutions. We get the best one. And then we go to the URL, we try to download it. Sometimes the fetch request fails, which is why it's in the try except block. And then here we just go through all the images that we found and repeat this over and over using our helper functions that we defined above. And then we compile all those vectors into a matrix and we store it as a file so we can use it later. And I think this process is a little complicated, so it's best understood just visually. So I have an example here. So first we have our image, we pixelize it, we transform it into a long list, and then we code that list as a vector of numbers, which basically encode the color of each pixel. And we do this for every image. And then this is our text processing pipeline. First, we take our text block. We have this clean function to remove all the HTML formatting. And then we have a list of stop words, which don't really contribute much to our model, so we skip over them. And then here we use this vectorizer to create unigram, bigram, and trigrams from the text, skipping over the stop words. And then we use this matrix that we made to give us a text vector embedding for every single item. And then we're storing this as an item vector dictionary. So we stored this as a file so we can refer to it later. And then we have some helper functions so we can get these variables easier later on.
In this part, I will walk through the baseline models we use for our rating prediction task. And I mainly use 4 baselines: the global mean, user mean, atom mean, and the bias model. Let's see how they work. And here I loaded the processed train and test data, as well as the user and atom index mappings created previously. Then I print some basic statistics like the train and test to reveal unique atom and users numbers. And we can see from the rating distribution that the data is distributed extremely sparse, which will matter how we explain the result later. And the first baseline is a global mean, which means no user or atom bias is included, just the same average rating number for every prediction. In our dataset, the global mean is 4.127, and the test MSE is 1.79. And this is our simplest baseline and serves as a start point. Next, we will compute the user mean baseline. And this means we compute each user's average rating. For example, if a user have always give 5 stars, we predict 5 for all his test atoms. However, because most users only have 2 reviews, so the user mean is noisy. As a result, the test MSE is 1.9, and which performs slightly higher than the global baseline. And next is atom mean. So it's a similar idea with the user mean. but now we use each item's average rating. And this works slightly better than the user mean with a MSE of 1.8. So next, let's move on to the strongest baseline, the user item bias model, which has a formula of alpha height UI equals R height UI equals alpha plus beta U plus beta I, where alpha is a global mean, beta U is a user bias, and beta I is an item bias. And we first group our ratings by user and by item. Then we use a coordinate descendant style update. We update alpha, beta U, and beta I repeatedly. And we also apply L2 regularization with lambda equals 5. So users or items with very few ratings don't get extreme bias values. And we set the max iteration as 20. And finally, we predict the test set using prediction equals alpha plus beta U plus beta I. And we can see the result is the best among all the baselines with a test MSE of 1.47. And I also add a comparison table. We can see the test MSE and test R MSE of the 4 baselines. And from the result, we can conclude that the user item means perform the worst because the data set is extremely sparse, while the bias model capture both user preference and item quality, so it performs the best. And this gives us a clear target. Any advanced model needs to beat MSE equals 1.47. This is all for the baseline section. Thanks.
Now I'll explain the matrix factorization model that we use and the hyperparameter search I performed to improve its performance. I'll start with the model architecture. Our model is based on matrix factorization with bias terms, and we extend it into a multimodal version by incorporating text embeddings and image embeddings for each item. The full prediction formula looks like this. R hat equals mu plus beta u plus beta I plus PU transpose QI plus lambda text times W text transpose TI plus lambda image times W image transpose VI. In simple terms, we're predicting a user's rating by combining user patterns, item patterns, and additional text and image features. Here, mu is the global average rating, beta U is user bias, beta I is item bias. PU is the user latent vector, QI is the item latent vector. Lambda is a weight, TI is text embedding vector, VI is image embedding vector. W text and W image are the projection vectors. So overall, instead of relying only on user item interactions, we use multimodal MF model that also leverages textual and visual information. Next, about training. We optimize the model using stochastic gradient descent. The loss function is the squared error plus L2 regularization. During training, we update 4 groups of parameters: user bias beta U, item bias beta I, latent factors PU and QI, text projection W text, image projection W image, and mixing weights lambda text and lambda image. For its training sample, we compute the MF part and the text part and the image part. We add those together to produce a prediction and then update parameters using the prediction error EUI. I perform a full brief search to find the best hyperparameters. I ran 72 experiments varying k, the latent dimension, learning rate eta, regularization lambda, and the number of epochs. The best configuration was k equal 100, learning rate equal 0.01, regularization lambda 0.01, epochs equals 10. Around 58,000 training samples and 14,000 test samples. Text embeddings had 128 dimensions. And image features were loaded into matrices aligned by item IDs. During the training, the MSE steadily decreased. By approx 20, the training MSE reached 0.1127, showing stable improvement. Finally, here are the evaluation results on the test set. Test MSE 1.3736, test RMSE 1.1720, test MAE 0.8871. Our baseline bias-only model had MSE 1.4740, so our matrix factorization model achieved about 6.8% improvement. In summary, combining matrix factorization with the text and image features leads to better recommendation accuracy, because multimodal features provide signals that pure collaborative filtering can capture.
So this is the evaluation section where we will be looking over our model in comparison to a couple baseline models that we made. So first, looking at just the MSE, which is probably our most useful metric for evaluating the model, we'll see that our model got an MSE of 1.36, which is a little less than 8% better than the bias model MSE of 1.47, which was the best out of all the baseline models we made. And then looking at the MSE and RMSE of all the models, we see that the global mean, user mean, and item mean models don't do very well with MSEs of 0.8 to 0.9. The bias model does pretty well actually, but it's still noticeably higher than our matrix factorization model. So looking at our metrics in a little bit more detail for our final model, again the MSE is 1.36 rounded. The RMSE is 1.16. The mean absolute value is just 0.8, and the R squared value is 0.25, which does seem a little bit low, but for recommender systems tasks, that's actually not bad at all. And then we have a couple other metrics here. The standard deviation is pretty much the same as the RMSE, which is expected. And then looking at the distribution of the ratings here, we can see that 75% of our ratings are between 4 or 5 stars, which is reflected by our accuracy here. We see that we do a pretty good job of getting those ones, but the far less common 1 to 2 star ratings, we do struggle quite a bit, and it does punish our metrics here, mostly because of the imbalance in the data set. And then we have a couple plots which can help us visualize our data. So firstly, we have our error distribution plot, which we have our predicted ratings minus our true rating. And we can see that this graph is a little bit right skewed, which does make sense because our model will tend to under-predict ratings as opposed to over-predicting them. Again, because most of our ratings are going to be between those 4 and 5 stars. So this means we may need to adjust our model because it might be underestimating things, but that can help us distinguish between the lower and higher rating reviews. And then here we're looking at the item and user popularities versus the mean absolute rating. And these graphs are, generally as we'd expect for both items and users. We see a pretty clear negative correlation, which indicates the more ratings we have, the better our predictor is at guessing the rating, which makes sense. And then finally, we have basically we're looking at the latent factor grouping. So, our model has, QBest, which has about 15,000 items in it, each one encoded by 20-dimensional vector, which basically encodes the item information. Now, obviously, since 20-dimensional, we can't visualize it, but this allows us to basically map it onto a 2D plane because distance is defined in higher dimensions. So the relative distance between two items in our matrix will be maintained here. So like if a point was twice the distance from one point to another, that relative distance will be maintained here. And this allows us to see which items are clustered together, which indicates that they're similar items. So looking closer at this, we can see little clusters which indicate these items are categorized similarly by our model. And this does show that our matrix is actually doing something, and that most of this error is probably due to these outlier items that aren't really in any cluster that can't really be categorized. And then we have this middle cluster, which is very common items that are fairly easy to predict by our model because it appears a lot. And then yeah, so outliers likely contribute to our model's error. And then we have our simple MSE, which is a simple metric, but arguably one of our most useful. We see that our final model does perform significantly better than all our baseline comparisons, though our bias model does perform fairly well, it's noticeably higher than our final one. So a couple things that can make it a little bit difficult for us to make this model was number one, the sparsity of the data set. and the balance of the data set as well, with most of our ratings being concentrated on those 4 to 5 stars. We can, in the future, incorporate more information into our model, notably time information, remove some more detailed textual information like length. The reason we didn't do it is yet because when looking at these metrics, we found that they aren't super great at predicting rating. But if we do, more detailed experimentation, we might find ways to extract, useful information from this time and text data that we may not have seen in our testing. So yeah, there's room for improvement for sure.
Let's discuss about the related work. So the Amazon reviews data set has been widely used for rating predictions, sentiment analysis, and recommendation systems. So our approach to building on 3 key methods: first, the matrix factorization by Korean, the Netflix price with the RMSE around 0.85, and then we follow the similar principle. And second, the bias model shows the simple baseline are effective on sparse data, which our MSE of 1.44 confirms. And lastly, the neural collaborative filtering uses the deep learning but requires dense data. So our MSE of 1.36 is strong given that our challenges that with the higher sparsity versus the typical 95 to 98%, the only 17,000 reviews versus million in benchmarks, and several cold start with a median 2 reviews per user. So overall, our finding align with the prior work. Bias models work well on the sparse data, regularization, which prevents the overfitting, and simple methods remain competitive. Thank you.